Hi, my name is Andy Arrowwood. This presentation describes most of the Sysplex functions that we implemented on our TCP/IP stack for comp server. So it's not a complete list, but it does cover a lot. Okay, so the first thing when talking about a Sysplex is to talk about the virtual IP address. Everything we do in the Sysplex is based on the virtual IP address. The virtual IP address identifies a server application independent of the physical interface. Instead, the VIPA is just associated with an application or a TCP/IP stack. This allows physical interface IP addresses to change on the fly without affecting the end user or existing TCP/IP connections from the client, in this case to the CICS application. And also this means that we don't need to change DNS hosts or anything like that. This allows interface resilience by removing an interface as a single point of failure. So in this example, as long as one of these interfaces is active, either interface 21 or interface 22, then the TCP/IP connection from the client to CICS remains active. Okay, so DYNAMICXCF Interfaces is another basic concept of our Sysplex management. With DYNAMICXCF Interfaces, dynamic connectivity is automatically established between all Sysplex members as they join the Sysplex. Using XCF messaging, each stack automatically learns of the other members in the Sysplex. The stacks share information about their DVIPAs, their dynamic VIPAs, their distribution. So every stack is aware of every other stack and aware of all the IP addresses on all of those stacks. To use DYNAMICXCF messaging, there's one of 3 DYNAMICXCF interfaces that may be activated. And that just depends on the location of one TCP/IP stack in relation to the other TCP/IP stack. So in this example, between stack 1 and stack 2, since both stacks are in the same LPAR, the DYNAMICXCF interface uses a function called IUT_SAMEHOST, which uses a very efficient way to send data between the 2 stacks. Between stacks that are on the same that are not on the same LPAR but on the same CEC or centralized processing complex, hypersockets can be used if it's configured. So in this example, stack 1 and stack 2 on LPAR 1 use hypersockets to communicate with stack 3 on LPAR 2. And then finally, between CECs, XCF signaling is used. So in the example, stack 4 is used to communicate with the 3 other stacks, or XCF signaling is used to communicate with the 3 other stacks. Okay, so the Sysplex does everything with dynamic VIPAs. There are 2 types of dynamic VIPAs. The first type are stack-managed DVIPAs. So with the stack-managed DVIPA, the activation of the DVIPA, the control of the DVIPA is managed by the stack, as the title indicates. The location of a DVIPA is transparent to the clients. The DVIPA identifies the TCP/IP application independently of the stack where the DVIPA is actually active on. A VIPA define statement is used to define the primary owner of the DVIPA. In this example, TCP/IP1 on LPAR 1 has a VIPA define statement for the DVIPA. And then VIPA backup statements on other stacks are used to define backup owners. A rank is configured. In the event of a failure of either LPAR 1 or TCP/IP1, then the stacks, one of the highest ranked backup stack in the Sysplex will take over. So in this example, since TCP/IP2 is configured with a VIPA backup statement of 200, outranking the VIPA backup statement on LPAR 3, TCP/IP2 would take over in the event of a failure. And again, as I mentioned earlier, DYNAMICXCF allows connectivity automatically between all of the members in the Sysplex. XCF messaging is used to actually send these different configuration statements between the stacks. So all three stacks are actually aware of which stack currently owns the DVIPA and which stacks back up that DVIPA. As I mentioned earlier, if there is an issue with LPAR1, and this would be an unplanned takeover, then as TCP/IP1 fails and leaves the Sysplex, the DVIPA automatically moves to TCP/IP2 since it is the highest ranked backup. TCP/IP2 takes over advertisement of the DVIPA, and so now all connections flowing from in this case this client, to the CICS application would flow to the stack on TCP/IP2. In addition, as TCP/IP2 takes over ownership of the DVIPA, it also sends connection resets on behalf of Stack 1 to reduce workload startup time for those connections which have to fail since they lost their connectivity to the application on TCP/IP1. Moving to page 6, so this covers the planned takeover scenario. So this is the same example, except in this case TCP/IP1 is restarted. Because it has a VIPA define statement, it'll automatically take over ownership of the DVIPA as it becomes active from TCP/IP2. As it takes over the DVIPA, it also handles routing for the existing connections that were established from the client to the application on TCP/IP2. Operator commands can also be used to allow a planned takeover without needing to change the configuration or use a variobay file. And so these are the two commands that are used. So if you deactivate a DVIPA on a stack, that basically removes the configuration statement for that DVIPA. So for instance, if we did a deactivate of the DVIPA on TCP/IP1, the VIPA define statement would disappear, and then allowing TCP/IP2 to take over. And if we did a reactivate, then again the VIPA define statement would be added back to TCP/IP1 and it would take back over. Okay, so the first type of DVIPA that we just talked about was a stack managed DVIPA. The next type of DVIPA is an application specific DVIPA. So with an application-specific DVIPA, the application controls the activation and the movement of the DVIPA. And it's used if the application needs to have exclusive access to certain resources while it's active. So typically this would be a database that really only supports having one user updating it at any one time. So in this example, CICS1 initially causes the DVIPA to be created on CICS3, and this can be done if the application does a bind explicitly to the DVIPA, or it can use a mod DVIPA iOptLocAL to create the DVIPA on the stack. If the application fails and it restarts on another LPAR, in this case stack 4, then as the LPAR fails on TCP/IP3, the DVIPA is removed, or the DVIPA is removed from stack 3 since the application is gone, and then as the application comes up on TCP/IP4, it would cause the DVIPA to be created, and now the DVIPA moves to stack 4. And a client can be configured to either use DNS to resolve the application name to the IP address, or it just can connect to a returned IP address if the CICS application connects to the client, or the clients can be configured to connect to a hard-coded address or a cached address. Going back now to stack-managed DVIPAs, an important type of DVIPA is a distributed DVIPA. So with the distributed DVIPA, allows multiple applications to be active at the same time on different TCP/IP stacks. And so this allows the different applications to all share the workload and be more efficient. The multiple applications all look like a single application to a client, since the client reaches any one of these applications by just using the distributed DVIPA. The Sysplex Distributor, which is owning the DVIPA and advertising it, makes a decision as to which stack will actually, or which application will actually receive the new connection and the new work for that workload. The data path from the Sysplex Distributor to the stack where the work is actually being distributed can use XCF interfaces, or it can use VIPA route. And certainly between KEX, you would definitely want to use VIPA route. So VIPA route, if VIPA route is configured, it basically says that although the packet is going into the Sysplex Distributor on TCP/IP1, as the connection is routed to, say, LPAR2 on TCP/IP2, it would just use an IP route that was configured for that purpose. And the IP route can make use of any of our interfaces, including OSA, allowing a very efficient way to move the data from the Sysplex Distributor stack to the backup stack. On the VIPA distribute statement, you can see we specify the DVIPA that we're distributing and the ports of the listening applications. We also have a feature called dynamic ports where the port can be left off, and that's used for outbound connections. So in that case, as an application binds to the DVIPA and a specific port, the Sysplex Distributor would learn about that port. As I mentioned, the Sysplex Distributor will load balance to the available applications, and it does this, how it selects the application depends on the distribution method, which I'll talk about in the next chart. The last thing to look at on the actual configuration statement is the dest IP statement. So the dest IP statement, which in this case says all, is saying that as connections are being distributed, that it will distribute to any application active on any stack. Instead of all, the specific XCF addresses of the backups of the other stacks can be configured, and in that case the distributor will only use those stacks when it's distributing connections. The Sysplex Distributor uses one of 5 methods for load balancing incoming connections. There are 2 distribution methods that are basically a static type of distribution. If round robin is configured, connections are evenly distributed to all targets. If weighted active is configured, the distributor's goal is to balance active connections to all targets based on configured weight proportions. And I'll talk about that one more on another chart. The other type of distribution uses dynamic WLM recommendations. So this uses a weighted round robin distribution based on a normalized WLM weight. Base WLM uses distribution based on received WLM system weights, and this is just simply based on a comparison of the displaceable capacity of lower importance work on each stack. So the stack with the most lower importance work would just automatically be preferred over another stack. With server WLM, these are server-specific weights, and so the comparison of displaceable capacity includes the importance level of the work that's being displaced. And I'll talk about that more in another chart. So in addition to including displaceable capacity, it also includes how well the application is meeting WLM service goals that might have been set up for that workload. Then the final distribution that's used when routing to TCP/IP stacks is Hor Standby. So if Hor Standby is configured, we only want to have one application being used at a time. So all connections would be directed to that target. Multiple hot backups would be configured, but they would only be used, or one of those backups would only be used if the currently active target was no longer available. And this just shows an example of how distribution occurs if you're using WLM recommendations. So in this example, normalized weights for the 3 stacks each stack represented by the XCF address have been determined to be 3, 2, and 5. So as 10 connection requests are received, 3 connections will be distributed to stack 1, XCF1, 2 connections would be distributed to XCF2, and finally 5 connections would be distributed to the stack defined by XCF3. When WLM, either base WLM or server WLM, is being used, there are additional factors that can be taken into account as distribution occurs. So the first one up there is the target server responsiveness fraction. And this is a metric that's based on the target connectivity success rate, and that's shown below. And that's basically saying, as the distributor routes connections to target 1, for instance, are the connections being received on target 1? So again, because we use XCF messaging, as a new connection is established, target 1 tells the distributor that the connection made it to target 1, and that causes an update of that target connectivity success rate. Another factor making up the target server responsiveness fraction is the server efficiency fraction. And this is a measure of how well the server itself is performing. As new connections are being established to target 1, is the server accepting that new work, or is the server not keeping up with the new work? Is the backlog queue of existing connections starting to accumulate? In addition, if the policy agent is used, we can also keep track of quality of service. And so this keeps track of retransmits and packet losses between a server application and the client. Another measurement that's being calculated is the connection establishment rate. And this just simply determines whether new connections are being established between the client and the target. This is a measurement that does not actually impact the target success server responsiveness fraction, but it is included in netstat displays, just so that if a user is seeing issues, they can look at that connection establishment rate and determine if connections are really being established or not. In addition, applications, if they're instrumented that way, can report the application health and their transaction completion status to WLM. And the health is basically a percentage between 0 and 100%, with 100% being perfectly healthy, and then an abnormal completion rate, which ideally you'd want, and that's an abnormal completion rate per 1,000 transactions. So ideally, you'd want the abnormal completion rate to be 0, meaning there were no abnormal terminations of a transaction, after 1,000 transactions were completed. Okay, now I'm going to talk a little bit more about weighted active, which I mentioned earlier. So with weighted active connections are balanced across available targets based on configured weights. Although WLM weights are not used to determine the target success rate and the WLM reported abnormal completion rate and health are considered, and so they would be used to actually adjust the weight or reduce the weight if there was an issue with any one of those 3 items. In this example, the weights have been configured as percentages, with 30%, with the desire being that 30% of all active connections will go to the stack defined by XCF1, 20% of the connections will go to the stack defined by XCF2, and 50% of the connections will go to the stack defined by XCF3. So these weights are also normalized, and so the result would be that as 10 connections are received, the initial distribution would cause 3 connections to go to XCF1, 2 connections to XCF2, and 5 connections to XCF3, preserving that desired percentage. Over time, as additional connections are added, connections may terminate. The distributor will constantly try to adjust the number of active connections to match the percentages. So in this example, 10 connections are being received, And what this is showing is that if, as those connections are received, the current number of connections is 300, 190, and 530, then, again, to target the goal of having 20% of the applications, the connections be on target on XCF2, all 10 of those connections would be directed to XCF2. So it would go from 190 connections up to 200. And as you can see, as 30 more connections are received, XCF3 wouldn't receive any, and those other 30 would actually be directed toward XCF1 or XCF2. Hot standby support was I mentioned earlier in this pitch. And when this distribution method is configured, the goal is that all connections will be directed to only one active target, and the other targets, again, are just hot standby, so they won't receive any connection requests. So the other targets are active so that the distributor knows that they're available, but the distributor directs everything to a preferred target server. If the preferred target server becomes unavailable, then the distributor switches over to the highest ranked backup target server. So you can see in the example below, XCF1 has been configured as preferred, and two other stacks could have been configured as backups. And the highest ranked backup in that case, XCF3, would be preferred. A target is considered not available when it's not ready, meaning there's no listener, or the route to that target is inactive, or if a health switch option is configured, then also the target server responsiveness fraction is considered, as well as the WLM application reported abnormal terminations per thousand and the server reported health. If the preferred target became unavailable, then if an auto switchback option is configured, the preferred target is used again when it becomes available, as long as the original reason for the switch was not because of health problems. And the assumption there is that if it's a networking issue or the server wasn't available, it makes sense to switch back to that preferred target when it becomes available. But if the issue is actually a problem with the application itself, that it's not healthy in some way, then if it appears healthy, that's probably because it's no longer processing new connections. And so we don't want to switch back to that target server because the implication is that it really probably is not available. Earlier, there was a question about how to prevent a target from receiving new connections, and then how to get the target to start receiving new connections again. So this is an example of if you want to use a preferred target after we've switched away from it because of health problems, you can cause it to switch back by using a very TCP quiesce and resume sequence. And again, those are the commands that cause the application to be quiesced, which means removed from consideration as a distribution target, and then resume mean we start fresh with that target, and even if the original reason why we stopped using preferred target was because of health, we'll start to use it again. Okay, so now I'm going to be describing some functions related to server WLM. So in general, when server WLM is used, one of the factors is as a connection request is received, based on the importance level of that workload, it looks at displaceable capacity. And so WLM rates or ranks all workloads by an importance level, with importance level 0 being the highest or most important, and importance level 7 being the lowest. So in this example, if I have a new Java workload and the importance level is level 2, then that work would displace lower importance workloads. So if I'm looking at LPAR1 and LPAR2, then from this perspective, they both have equal amounts of displaceable service units. However, you'd really want to prefer LPAR2 because the work that would be displaced on LPAR2 is lower importance work than the work that would be displaced on LPAR1. So to do this, an importance level weighting parameter can be configured. So in this example, if an importance level weighting parameter of 0 is configured, then the importance levels of the lower importance work is not considered. However, if importance level 1, 2, or 3 is configured, then the Sysplex distributor is will start to prefer the stack with the lower importance work, and the amount of aggressiveness depends on that IL weighting factor, 1, 2, or 3. Okay, so moving on past importance level weighting. Another thing that WLM considers is specialty processors. So specialty processors are processors that are deployed and exploited by targeted workloads on ZOS. There's a ZAP processor type, which is a Z-series application assist processor, and that's for Java workloads such as WebSphere applications. And then there are also ZIP System-Z integrated information processors, and they can be for DB2 workloads or ZOS IP security workloads. So one concern when using specialty processors is crossover cost. So crossover cost is when you want to have an application use, say, a lot of ZAP processing power, for instance, but that ZAP processing power or service units aren't available, and as a result, instead of using a ZAP service unit, you end up having to use the general processor in its place. So with crossover cost configured, the comparison of displaceable capacity will consider the desired or the actual use pattern of the processor by a workload against the available service units for each processor on each LPAR. So in this example, we have a Java workload that's designed to use 10% CP processing and 90% ZAP service units. So as the workload runs, WLM automatically determines that usage pattern. So it sees that as this application is running, that this is how the usage pattern is. It determines this is what the usage pattern is. And the reason I'm bringing that up is it's not a configured parameter. It's just something that WLM is able to determine as it watches how service units are consumed. So in this example, we have 1,000 service units of displaceable capacity on each LPAR, but on LPAR1, there are only 100 service units of ZAP processing service units. So ideally, you would want to prefer LPAR2 for this type of application. So a crossover cost or a proc X cost parameter can be configured, and that would penalize LPARs that don't have enough service units to allow the application to run entirely on the ZAP processor. Instead of having, it'll penalize them for having to run on the central processing unit. So with a higher processor crossover cost value, WLM would, prefer LPAR2. So if the ZAP and ZIP processor crossover cost is a 1, it means that there should be no penalty. So in that case, as a Java workload arrives, it would prefer LPAR1 and LPAR2 equally. However, if a higher crossover cost is configured, say ZAP5 and ZIP5, then as the Java workload arrives, it would prefer LPAR2 over LPAR1. This function is actually supported for base WLM, and to do it for base WLM, you would actually need to configure the desired use patterns, since there's no way for WLM to, since when base WLM is being used, there's no way for WLM to know what workloads are going to use an application. Okay, another function related to Sysplex distribution is timed affinity. So if timed affinity is being used, then when the target for an initial connection from a client is determined, the configure distribution method is used to pick that target. However, after that target is picked, then if time to Affinity is configured, that same target is used for new connections from that same IP address. So in this example, connections coming from 201.81.10.1 start using CIX2, and connections from the client 199.81.10.2 start using CIX4. So at that point, all new connections would continue in that manner, with 10.1 going to CIX2 and all new connections for 10.2 going to CIX4. When the last connection from the client ends, then the time to Affinity still continues for a little while, and that's based on the configured time to Affinity parameter. So for instance, the time to Affinity parameter is 5, then it means when the last connection from a certain client ends, it'll still keep the affinity for 5 seconds. So if the client starts a new connection within that 5-second period, even though there aren't any current connections to the priorly used application, that connection will still go to that application. And this is used with base and server WLM as well as weighted active and round robin. Okay, another function associated with Sysplex distribution is optimized local routing. So when OPTLOCAL or optimized local routing is configured, the intent is to prefer a local server if the client is to prefer a server on the same stack as the client. So in this case, the Tier 1 Sysplex distributor would choose, say, WAS1, and if OPTLOCAL is configured, the goal would be for the Tier 2 Sysplex distributor to prefer TCP/IP1 as the target for new connections from WAS1. And OPTLOCAL basically has 3 settings. If OPTLOCAL 0 is configured, then the local server will be used if there are no problems with the backend server. Again, so the server is available, the backlog queue is not growing, there are no issues with abnormal transactions or server health, then the local server continues to be used. Or if the connection was from WAS1, then the backup tier, the backend tier CIX1 would continue to be used. OPTLOCAL 1 says to use the local server if there are no server problems, which are all the conditions above, and also to only use that server if the WLM raw weight for that server is 0. And then finally, OPTLOCAL 2 through 16 says to use the local server if there are no server problems, the WLM raw weight for the backend server is not 0, and the normalized weight times that OPTLOCAL value is greater than the normalized weight of the servers that are not local to the TCP/IP stack. Alright, so this next chart kind of continues with that goal of trying to keep the tiered connections local to the same stack. So in this case, we added something called application awareness. So the Tier 1 load balancer is actually using information about the backend Tier 2 applications when it selects a target. So in this configuration description, the 2 tiers for basically Tier 1 is DVIPA1 and Tier 2 is DVIPA2, and they're linked by this group name, or group 1. So when a distribution target is selected, you can see that although WAS1, 2, 3, and 4 all have the same WLM weights, that WAS1 is actually the least preferred, and that's because its backend server has a WLM weight of 1. So what's being done is we're adding the combined weights of both tiers on the local stack and then just dividing by 2. And so that causes distribution from to not prefer WAS1, but instead to prefer WAS2, 3, or 4. Okay, another optimization beyond the desire to keep applications local to a stack is to keep tiered applications local to a CPC or KEC. So if CPC scope is configured, then there's actually two Tier 2 VIPA distribute statements that are used. So in this example, there are 3 distributors involved in distributing connections. There's the Tier 1 distributor, Tier 1 SD, and then associated with each KEC or site, there's 2 Tier 2 distributors. And so if VIPA backup statements are always, as a VIPA moves, for instance, between the Tier 2 distributor on CPC1, a backup would have to be on either TCP/IP1 or TCP/IP2. So when the Tier 1 Sysplex distributor chooses to use WAS1, the Tier 2 distributor will use either choose either KIX2, or in this case it would use KIX2 because the KIX1 weight is 0. And again, so we're using the combined weights to select the initial target. But then once that initial target is selected, now we're moving to the Tier 2 Sysplex distributor. The Tier 2 distributor will keep the connection local to that CPC and just prefer the server with the best weight. So this allows better performance. Since we're keeping the data flow within the CPC, we can make use of hypersockets. This also could reduce security requirements as well, since the data flow is staying within a KEC. Okay, so the next thing I'm going to talk about is Sysplex distributor support for DataPower. So the Sysplex distributor can be configured not only to load balance connections to ZOS applications, but it can also be configured to load balance applications on DataPower appliances. The distributor starts out by sending the VIPAs, ports, and a polling interval to each DataPower application. The DataPower application configures those DVIPAs as non-advertised DVIPAs, or similarly to how our target stacks configure their DVIPAs as non-advertised DVIPAs. And then the DataPower appliance sends weights to the distributor, and this allows the distributor to load balance appropriately between the DataPower appliances based on available capacity. Connection states are also sent by the DataPower appliance to the distributor. And so because the connection states are sent, this allows failover. So a distributor can take over, and that distributor knows for the existing connections which DataPower appliance to route each connection to. GRE is used to route to the DataPower appliance, and this allows the Sysplex distributor to be bypassed on the return path back to the client. So the Sysplex distributor can route to DataPower based on processor availability on DataPower, and to do that it uses a new distribution method called target control distribution. So in this example, GRE is configured, and GRE being configured indicates that the target is a DataPower appliance and not a ZOS target. And because GRE is configured, it means that the distribution method of target control can be selected. In this example, the distributor will distribute it to the DataPower appliances based on weights received from those appliances. And you can see in this example we could have Tier 2 distributor routing from the DataPower appliances to the back-end LPARs. And this allows for simplified administration, since all the distribution is being controlled by a Sysplex distributor, either the Tier 1 Sysplex distributor or the back-end Tier 2 Sysplex distributor. We also have a multi-site support availability for DataPower, and this is similar to the diagram I showed earlier when we were talking about Tier 1, Tier 2 CPC optimizations, again, where the goal is to try to keep the distribution from the WAS applications on the same tier as the CPC. And so with this multi-site support for DataPower, we're trying to do the same thing. So the Sysplex distributor learns the associates DataPowers with specific KEX, and then it uses the DataPower weight as well as the weight of the back-end application to determine an overall weight to route connections to. So in this example, because target-controlled routing is being used, the Sysplex distributor is aware that DataPower 3 has a weight of 500 and DataPower 4 has a weight of 900. So between DataPower 3 and DataPower 4, the Tier 1 Sysplex distributor would prefer DataPower 4 over DataPower 3. However, because we're also getting weight information from the back-end appliances on the same KEX where these DataPowers reside, the overall weight is being adjusted. So if you look at the back-end WLM weights on CPC1, you can see that the combined weight of WAS1 and WAS2 is going to be 12, as opposed to the combined weight of 20 on CPC2. And so that causes DataPower 3 and 4 to be preferred over DataPower 1 and DataPower 2. And so looking at the final normalized weights that are used, DataPower 1 and DataPower 2 have a lower weight than DataPower 3, and that's 5 to 3. And then finally DataPower 4 is preferred over all 3 with a weight of 9. Another function supported by Sysplex Distributor is SYSPLEXPORTS. And so the goal for SYSPLEXPORTS is that we want to make sure that all outbound connections from a DVIPA use a port that's unique within the entire Sysplex. So for example, if the applications on TCP/IP1 and TCP/IP2 represented by a distributed DVIPA 10.1.1.1, if we had an outbound connection from these KICS applications to the client IP address and we were not using Sysplex ports, then it's possible that TCP/IP2 and TCP/IP3 would choose the same ephemeral port for each application to use. And if we did that, then basically we would have a situation where we didn't have any data integrity anymore because we couldn't guarantee where a packet was going to arrive, since the applications would have the same for tuple. If Sysplex ports is configured, then the coupling facility manages source ports for that DVIPA, and it allocates those DVIPAs to a stack in blocks of 64 ports. So in this example, if you look at green, the green port range 5001 to 5064, the coupling facility has allocated those ports to TCP/IP2 for this DVIPA, and then the coupling facility has allocated the blue port range to the KICS, well, to the TCP/IP3 stack. And so now when a KICS application attempts to establish a connection to the client IP address and the same port 3001, if it's coming from TCP/IP2, the source port is going to come from the 5001 through 5064 port range, and the outbound connection from the KICS application on TCP/IP3 is going to use a port from the blue application port range. Okay, getting close to the end of my presentation, another thing I wanted to talk about was Sysplex-wide security associations. So the Sysplex distributor supports IP security workloads that are targeting distributed DVIPAs. The distributor handles the security association negotiation and refresh. It uses the coupling facility for DVIPA takeover to keep track of tunnel negotiation information and the tunnel's sequence number for shared tunnels. And again, in this configuration, you would want to use Sysplex ports to ensure that unique source ports are used for outbound connections from the distributed applications back to their client. Okay. Another function I want to talk about was Sysplex autonomics. So with Sysplex autonomics, the intent is to be aware of problems in the Sysplex to be able to detect problems and recover from problems in the Sysplex. So with Sysplex Autonomics, each stack is configured to try to detect problems with Sysplex Distribution or with our DVIPAs. So there's time-dependent monitoring. So for example, if that timer 60 seconds is configured, then every 60 seconds we'll do time-dependent monitoring, verifying that OMP route is still active, VTAM is active, that storage, either common or private, is not critical during that interval, and also if important interfaces are up, which is the red. Monitoring, we can monitor important interfaces, and if dynamic routes is configured, we can monitor that the routes over those interfaces are active. The delay join parameter would actually cause the stack to not join the Sysplex if OMP route was not active. Non-time dependent monitoring includes Sysplex if there was an abend in our Sysplex code. To recover from a problem that is detected, if recovery is configured, then that stack will automatically leave the Sysplex. It'll always issue an actionable message alerting an operator about the problem that it detected. And then if it's a recoverable problem, meaning maybe OMP route wasn't available or VTAM wasn't available, then monitoring continues for those recoverable problems. If auto rejoin is configured, then when the problem clears, that stack would automatically rejoin the Sysplex. Okay, the last thing I wanted to talk about was subplexing. So subplexing allows isolation of multiple secure areas. So without subplexing, IP connectivity using DYNAMICXCF is established to all stacks in the Sysplex, and dynamic IP address discovery occurs over the entire Sysplex. Coupling facility resources, VTAM generic resources, multi-node persistent sessions, Sysplex port resources, SWSA resources span the entire Sysplex. If subplexing is used, then IP connectivity, all of these functions, dynamic IP address discovery, use of coupling facility resources is located within the TCP/IP subplex. So in this example, if you look at TCP/IP1 and TCP/IP2, they're part of a default subplex, EZB TCP/CS, and so information about their localized Sysplex is only established between LPAR1 and LPAR2. And then another Sysplex group has been established called an intranet production IP subplex. And so in this subplex, information about the Sysplex is only sent between the stacks on LPAR3, LPAR4, and LPAR5. And then finally, a third subplex has been defined for stacks on LPAR4 and LPAR5. And so those stacks would only exchange information about the Sysplex between themselves. All right, so this concludes my presentation. I know it did cover a lot of information. If you want to find out any additional information on the topics I've described, our configuration guide is a very good resource that explains a lot of these functions. And again, you can always send me a question if you'd like.